Welcome to Hired in IT. Our mission is simple: help you build the skills that employers actually want. Whether you're trying to land your first IT job, switch careers, earn a promotion, or increase your salary, we're here to help. Every video is thoroughly researched and designed to make complex IT topics easy to understand. If there's an IT topic you'd like us to cover, leave a comment below. We may turn your suggestion into our next video. Turning IT knowledge into career opportunities. A customer support AI for an insurance company pulls the wrong policy from its vector database, mixing up flood coverage with earthquake coverage. The customer is told they're fully insured right before a disaster. The Python code? Perfect. No bugs. The retrieval? Completely off. This is why the vector database, not the code, determines AI reliability. By the end of this video, you'll have 3 career-changing takeaways, and we're starting with a concrete benchmark. Right after this overview, I'll run a recall at 10 test on Pinecone's free tier to show you exactly how a poor chunking strategy can slash retrieval accuracy by over 30%. First, why vector databases are the real bottleneck in AI apps. Second, how to choose and tune a vector index for RAG. And third, the data engineering shift that gets you hired in 2026, including the exact steps to build a working RAG pipeline this week. Think of it like this. Python logic used to be the star of the show, but LLMs have commoditized all that scripting. The new competitive edge is how you structure the external memory, the vector database. Systems like Pinecone and Milvus now handle massive vector collections with fast retrieval, shifting the bottleneck from your code to your indexing strategy. This diagram shows the shift from writing functions to architecting retrieval. In 2020, an AI engineer was essentially a Python expert. You wrote every bit of logic, manually crafted prompts, and relied on exact keyword matches in SQL. Fast forward to 2026. The LLM handles the boilerplate. Today, a retrieval architect uses tools like Pinecone or Weaviate to manage vector indexes and measures success with metrics like Recall 5. Python mastery is being automated away. Retrieval architecture is not. Picture this. You've written a flawless Python function. It calls the LLM with perfect syntax, handles errors elegantly. But the output is dangerously wrong because the vector database retrieved a chunk about banana farming when the user asked about a banana bread recipe. The code was immaculate. The retrieval was garbage. Most hallucinations aren't from bad logic, they're from bad context. Recall at K is a standard metric that measures what fraction of actually relevant documents show up in the top K results. So if there are 5 relevant documents and the database retrieves 3 of them in its top 10, recall at 10 is 60%. That's the number you need to be auditing. The most common mistake? Engineers test only the code, never the retrieval precision. If you're not auditing your recall at K, you're building on quicksand. It's time to pivot. Stop identifying as a script engineer. The role of retrieval architect is the new gold standard. Your first step? Audit your current RAG pipeline's recall at K. Don't just test if the code runs. Measure how often it retrieves the right chunks. That's the metric that separates the pros from the pack. Let's see it in action. A user searches affordable smartphone with great camera. SQL looks for those exact words. If the product description says, iPhone impressive photo quality, great value, SQL's like query misses it completely. But a vector database converts both query and documents into embeddings, a numerical representation of meaning. and cosine similarity, which measures how much two vectors point in the same direction, catches the semantic match. That's why you need vector databases. SQL simply can't understand meaning. Here's the foundation of all of this: an embedding. Take the word cat. Pass it through an embedding model, and out comes a list of numbers, like 0.02, 0.19, -0.05, and so on. This list typically has 768 or 1,536 dimensions, each number representing some latent feature of the word. Similar words get similar vectors. That's why we can search by meaning. Now, the math that matters more than decorators. Here's cosine similarity in 3 lines of Python. We compute the dot product and divide by the product of norms. This number tells you how similar two meanings are. If you're still spending your time mastering Python syntactic sugar, you're optimizing the wrong thing. The Python master knows every advanced trick in the book: decorators, async tuning, C extensions. But none of those skills prevent hallucinations or reduce retrieval latency. The retrieval architect thinks differently: cosine similarity, HNSW parameter tuning, and chunking strategies that actually move the needle. These are the skills hiring managers now pay a premium for. Picture this: a banking chatbot that confidently tells a customer you owe a $5,000 early withdrawal fee because retrieval returned an irrelevant page about wire transfers. The LLM hallucinated, and no Python script could have stopped it. That failure is exactly what RAG, retrieval-augmented generation, prevents. RAG is the data engineering pattern that first grabs the most semantically relevant chunks from a vector database, then feeds those facts directly into the LLM's prompt so its answer is grounded in evidence. The pipeline is simple. A user query becomes an embedding. That vector hits an approximate nearest neighbor index to pull the top K document chunks. Those chunks get loaded into the prompt alongside the original question, and the LLM generates a factual answer. The magic is not in the Python glue code, it's in the vector search step. If retrieval pulls the wrong chunks here, every downstream piece of logic is useless, no matter how flawless the rest of the code looks. A legal AI assistant just missed a fatal contract clause because it was dumped into the prompt as one giant 40-page document. The clause was smack in the middle, and LLMs are notorious for ignoring the middle of long inputs. Researchers call this the lost in the middle effect. The model pays high attention to the beginning and the end, and far less to everything in between. If you shove all your raw documents into the LLM's context window, you're practically begging it to overlook the exact piece of evidence it needs. The retrieval architect's solution? Don't let the prompt become a novel. Use metadata filtering to pull only the most relevant bite-sized chunks. When you pre-filter by date, source, or topic before retrieval, those injected snippets are guaranteed to be both petite and pertinent, keeping them squarely in the high attention zone and completely sidestepping the lost in the middle trap. Here's how a retrieval architect stops irrelevant chunks before they ever enter the prompt. When you insert vectors into Pinecone, you attach plain old metadata like genre, date, or source. Later, the query explicitly filters by that metadata, so the search only considers documents that match it. The metadata filter that restricts results to the science genre means the vector database will only return chunks from science-tagged documents, eliminating off-topic noise, saving latency, and dramatically lowering the hallucination risk. Here's the concrete habit that separates beginners from pros. Every time you upsert a vector, always attach at least 3 metadata fields: date, source, and topic. That one step makes your retrieval pipeline resilient instead of fragile. Here's what nobody tells you about retrieval-augmented generation. Improving retrieval precision can yield accuracy gains that rival or even surpass what you'd get from just throwing more parameters at your model. Yet many engineers overlook this. Most AI engineers still obsess over Python orchestration, tweaking prompt templates, chaining library calls, fine-tuning code until every line is a decorator-laden masterpiece, while they barely touch the vector database settings. Garbage in, garbage out. If the retrieval layer fetches off-topic chunks, the fanciest LLM on the planet will still spout nonsense. That's why the rest of this video is not about Python. It's about indexing strategies, chunking decisions, and metadata hygiene. The real lever for killer AI applications sits squarely inside your vector database, and we're going to tune it. Every vector database offers different indexing strategies, and the choice directly shapes performance. HNSW builds a graph index in memory, delivering fast queries ideal for real-time apps. Discan keeps the graph on SSD, reducing memory costs while still achieving high recall. Brute force flat search, by contrast, checks every vector, giving exhaustive coverage but becoming too slow at scale. These aren't Python tweaks. They're architectural decisions at the database layer. Lose unnecessary latency here, and no amount of Python can buy it back. HNSW. Hierarchical Navigable Small World organizes your vectors as a graph, with long-range edges that leap across the space and dense local connections for fast traversal. It's like a social network for data points. Parameters like M and EF construction let you tune the speed recall trade-off precisely, and this graph lives inside the database, not your Python code. While some vector index structures require the entire graph to reside in memory, Discan flips the approach. The graph stays on solid-state storage, and only a small pruned search frontier is pulled into RAM. This makes it possible to serve queries against massive vector collections on relatively low-cost hardware, rather than requiring racks of high-memory instances. For enterprise AI teams, that can mean the difference between a proof of concept and a real production system. Understanding these architectural trade-offs, when to prioritize speed, when to save cost, is exactly the kind of data engineering judgment that Python-only engineers never develop. The way you break documents into chunks might be the single highest leverage tuning knob in your whole RAG pipeline, and it has nothing to do with Python. Do it badly, and your vector database will store broken fragments that mislead the LLM. This checklist runs through the hard-won rules. Use semantic boundaries like natural paragraphs, overlap the slices so the model doesn't lose transitional context, keep chunks around 500 tokens, and for the love of retrieval precision, never ever split in the middle of a sentence. Actionable next step. Pick one data set, try 3 different chunk sizes, say 200, 500, and 800 tokens, and run a recall evaluation to find the sweet spot for your own data. Recall simply means, out of all the truly relevant chunks for a query, what percentage did your search actually return? You want it above 80%. This one experiment teaches you more about AI engineering than polishing a Python decorator ever will. Here is a mistake that silently destroys retrieval quality. You index all your documents using OpenAI's text embedding Ada002, but later, because Cohere's Embed v3 looks faster, you embed each user query with that model instead. On your screen, the vectors look like identical lists of numbers, but in vector space they live in completely different coordinate systems. Cosine similarity between a vector from model A and a vector from model B can be misleading. Each model creates its own vector space, so direct comparison might not reflect true semantic similarity. The fix is brutally simple. Always use the exact same embedding model for indexing and for querying. Period. Embeddings are not interchangeable. The retrieval architect knows this, while the Python-only engineer calls a random model and wonders why the answers are garbage. Let's look at the relative time costs in a typical RAG pipeline. The Python function calls that wrap the LLM contribute almost nothing. They're a tiny fraction of overall latency. A well-tuned vector search with an HNSW index stays lean, adding just a small slice. But if your vector index is misconfigured and doing a brute force scan over millions of vectors, that search time can balloon, sometimes eclipsing the LLM's own compute time. A junior engineer might spend hours micro-optimizing Python code, but that shaves off a fraction invisible on this chart. The only lever that truly moves the needle is the indexing strategy. In practice, switching from brute force to HNSW indexing can dramatically reduce retrieval latency, turning a slow product into a fast one. The exact numbers vary by workload, but the pattern holds. Python performance is a rounding error. Retrieval performance is your architecture. Modern AI roles demand data engineering skills that go beyond Python scripts. Version control tools like DVC let you track your vector datasets, so you can reproduce the exact state of your embeddings when debugging. Managed vector databases like Weaviate support sharding to partition indexes across nodes, and many cloud-based solutions provide similar capabilities, enabling parallel queries at scale. Pure Python alone can't handle that complexity. Start exploring data versioning and sharding concepts this week to think like a data engineer. Here's the uncomfortable truth. Low-code orchestration platforms are reducing the need for custom Python glue code that used to be your job. On the left, the old way. Hundreds of lines of custom code to chain LLM calls, handle errors, and rotate keys. On the right, the new way. Visual flows where you connect blocks and deploy instantly. But here's the key. These tools still rely entirely on your vector database design and chunking strategy. The Python may shrink, but the engineer who understands index tuning, metadata filtering, and embedding alignment is irreplaceable. That's your moat. Test your retrieval IQ. Checkpoint. Pick the right index. The job market reflects this shift. Demand for vector database skills in AI engineering is rising rapidly, while traditional Python skills alone are no longer a differentiator. Analysts predict the vector database market will grow at a compound annual rate of over 20% for the next decade. That means the person who designs the memory architecture, not the one who writes the loop, is the one getting hired. If you can architect a retrieval system, you're already ahead of 80% of applicants. Here's your career pivot in 4 concrete steps. Step 1. Pick Pinecone. Its free tier lets you spin up an index in minutes and learn to insert, query, and scale it completely. Step 2. Build a real RAG pipeline that includes metadata filters, because without those, your chatbot will recommend dog food to cat owners. Step 3. Benchmark your query latency, then tweak HNSW parameters like M and EF construction to hit the sweet spot for your scale. Step 4. Experiment with different embedding models and chunk sizes, and measure how they affect retrieval recall. This isn't theory, This is the practical roadmap that transitions you from a Python scripter into a retrieval architect. Most production search engines don't rely on vector search alone. Think about a user searching for Jaguar. They could mean the animal or the car. Keyword search with BM25 will catch the exact term but miss panther. Semantic vector search finds related concepts but may mix domains. Hybrid search combines both. A sparse branch using BM25 for exact keyword matching, and a dense branch using vector embeddings for contextual similarity. The fusion layer, often using a normalized scoring formula like reciprocal rank fusion, merges results into a single high-quality list. Weaviate natively supports this hybrid approach, making it a go-to for e-commerce and enterprise Q&A. This is the kind of architecture you design as a retrieval architect, not something you can slap together with a Python script. Here's a concrete technique that separates a retrieval architect from a scripter: multi-vector retrieval. Instead of embedding a whole document into one vector, which loses granularity, you create separate embeddings for the title, summary, and body of each document. When a user queries, you search against each vector space, then merge the rankings with reciprocal rank fusion. This algorithm doesn't need to normalize scores across different embedding models. It simply uses the ranks and a constant k to compute a combined score. The code on screen shows the fusion function and how to call it for 3 result lists. Implement this today and you'll immediately improve recall on long structured documents, something no off-the-shelf LLM can do on its own. Let's walk the full life cycle of a vector, from raw data to query answer. It starts with your data source: documents, logs, images. First, you chunk it. Inefficient chunking can add latency if you're not careful. Next, you embed those chunks through a model like OpenAI's text embedding 3small, producing high-dimensional vectors. These get inserted into your vector database, which then builds an index, HNSW or DiskN, to enable fast nearest neighbor search. When a user query comes in, it goes through the exact same embedding model, never mix models, then hits the ANN index, optionally filtered by metadata like date or category, and returns the top K most relevant chunks. Every single step is a potential bottleneck, and understanding this pipeline is what makes you a data engineer, not just a coder. Quick recall: checkpoint, the real hallucination source. Picture this: an e-commerce pet supply site rolls out an AI chatbot. A cat owner asks for food recommendations, and the bot cheerfully suggests a 40-pound bag of high-protein dog kibble. Why? Because their vector database indexed all pet product reviews as a single massive chunk without any metadata. Dog food and cat food reviews were bundled together, so the semantic search returned the wrong context. A retrieval architect would have attached a metadata field, pet type, to every vector. Then, before the LLM ever sees the prompt, a simple filter excludes all dog products. Noise in the prompt kills accuracy, and you're the one who prevents that noise. That's the difference between a data engineer and a Python coder. It's 9 a.m. at a major news site. A breaking story hits: a massive earthquake in Japan. Within milliseconds, the system knows every user who has previously read articles about natural disasters and instantly surfaces relevant live updates on their homepage. That's not a Python script refreshing a cache. That's real-time vector streaming. The architecture is event-driven. Every new article, user click, or search query flows as an event into Apache Kafka, a widely used streaming platform. A lightweight embedding microservice consumes those events, generates a high-dimensional vector, and upserts it into a managed vector database like Pinecone. The personalization engine then queries that constantly evolving index to serve the freshest content. With Kafka's low-latency delivery and a fast vector database, you can serve truly fresh recommendations. Here's your prototype for this week. Spin up a free Kafka cluster on Confluent Cloud. Write a simple producer in Python and use a vector database like Pinecone to store embeddings. That's a live, real-time vector pipeline you can explore and potentially demonstrate in an interview, and it leaves static Python batch scripts in the dust. You don't need to learn 5 vector databases right now. Pick one that matches your scale. Pinecone is the easiest managed option. Spin it up and start building in minutes. Weaviate gives you native hybrid search, fusing BM25 and vectors out of the box. Milvus is the open-source giant, built for large-scale vector search. Thais is ideal for local research and prototyping. And Cohere Embed offers a top-tier embedding model you can plug into any of the above. Choose one tool this week and build something real. If you take away only 3 things from this video, make it these. First, the industry isn't hiring Python wizards anymore. It's hiring retrieval architects who design the external memory that AI models depend on. Second, the fastest way to make your AI output trustworthy is to nail the indexing layer. Choose the right ANN algorithm, enforce metadata filters, and never let an irrelevant chunk poison the prompt. Third, start thinking like a data engineer. Version your vector stores, shard for scale, and treat noise reduction as a first-class metric. The retrieval architect owns the AI's brain. And now for the one micro step that turns this from theory into action. Right now, before you watch another video, open a new tab and sign up for a vector database service like Pinecone or Weaviate, then create your first index. It's a quick way to get hands-on, and you'll have a live vector store where you can experiment with everything we just covered. That single index is the start of your retrieval architecture portfolio. Here's your concrete plan. About 2 hours, no fluff. First, sign up for Pinecone's free tier. Next, grab 100 documents, maybe a small Wikipedia dump, and use OpenAI's embedding model to vectorize them. Then wire up a simple semantic search with one metadata filter. Finally, run a few dozen queries while varying the HNSWEF parameter, and watch how latency and recall trade off. That one experiment will teach you more about retrieval performance than any lecture. This is your portfolio project. No Python decorator can replace it. If you want to see exactly how these vector database and data engineering skills slot into a broader IT career path, grab the free IT career roadmap. The link is in the description. It's the exact resource I built to help you stop guessing and start moving. And one question before you go: which vector database are you going to try first? Pinecone, Weaviate, or Milvus? Drop it in the comments. I read every one. Thanks for watching, and I'll see you in the next one. Remember, careers aren't built by watching videos. They're built by applying what you learn. Pick one thing from today's lesson, build it, document it, and share it. That's how you get hired. Thanks for watching Hired in IT, where we're turning IT knowledge into career opportunities.